Hello there, this is Ms. Nakayama, and today's lesson is 3.5, Exponential Growth and Decay. This is the last lesson of our chapter, and this is the application of what we've been doing of exponents and logs this chapter. So, what we're going to talk about is modeling exponential growth and decay. As I said, that is the application of exponents and logs. So, just to refresh your memory or make you aware, we have a mathematical model for exponential growth and decay. And it says f of t equals a sub 0 e to the kt. The one I actually prefer to use is a equals a sub 0 e to the kt. K, if k is greater than 0, then your entity is growing. If k is less than 0, then your entity is decaying. Okay, that's the biggest deal. Look at these graphs down here that we have. Okay, growing right here means it's increasing and getting bigger and bigger each time as time passes, and decaying is decreasing, getting smaller and smaller each time. Exponential growth, exponential decay. One of the things I want to point out about this graph, y'all, is notice that there's not an arrow at a sub 0. A sub 0, okay, is your original amount. That's the amount at time t equal to 0. T equal to 0 is time equals 0. That's the beginning amount. That's the original amount. And it doesn't make any sense for time to be negative. So that's always going to be our starting point, which is our y-intercept on a graph. Okay, so as I said, it is when time equals 0. And if k is positive, it's representing the growth rate. If k is negative, then it's representing that decay rate. All right, look at these examples. First off, example 1. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Use the exponential growth model, this right here, in which t is the number of years after. And remember, I'm always really big about paying attention to those labels because it just makes it easier to know where to plug numbers in. So in which t is the number of years after 2000, define the exponential growth function that models the data. So we need a function that models the data, and that means that you're going to have to go find a number to put in right here and a number to put in right there for k. So when you read it, a sub 0 is the initial population. Well, they just told us in 2000 that the population was 807 million. So that's my a sub 0. And if they tell me the ending population, which in this case, they give me another number, so that's my a value. And I can find t. I know t because I know this happened in 2011. So 2011 minus 2000 is going to be 11, and so t is equal to 11 in my problem. So I'm going to start with that model. A equals a sub 0 e to the kt, and then I'm going to plug in the numbers I know. That means my final amount was 1,052. My initial was 807 in millions, y'all. So the millions, I just got to know to put that back in the answer if I'm asked the population. 807, then e to the kt, and t we determined was 11. Okay, so you're solving for the variable that's in the exponent. And if the variable's in the exponent, y'all, that means that we're going to use logs. But I cannot use a log until I have gotten rid of that coefficient. We talked about that a lot in the previous lesson in solving logarithmic equations. So I have to divide first by 807. And you can pick up your calculator if you want. I don't like to, so I just leave it as 1052 over 807. And now at this point, I have nothing, no coefficient except for 1 in front of my exponential expression, e to the 11k. So now I'm ready to take the log of both sides. So when I take the log of both sides, on the left I have ln of 105 over 87, but the ln of e, those are composing inverse functions, and that's going to be equal to 11k. So then to solve for k, I just have to divide by 11, put that in your calculator in one fell swoop, and you get that k equals 0.0241. One way to check yourself, y'all, k is a positive number, and they told us that it was exponential growth. So that means I know that I've done things somewhat correctly. And you can plug it back in to see. However, so I need a growth function. So as I said, I'm using this model right here that I've highlighted in yellow, and I'm going to plug in, I'm going to have A equal to 807 E, and K is 0.0241 T. And that is my model. So you got to pay attention to the question. If they want a model, that's the answer to your question. Now the second part says, by which year will Africa's population reach 2,000 million, okay, or 2 billion? Well, 2,000 million is the same units we've been using in the other problem. I mean, in the other part of the problem. That's what my model uses. So that's why I've got to plug in 2,000 for my final A value, because that's when I want to know when it will reach that. Again, I have to divide both sides by 807. And now I'm going to take the ln of both sides. And remember that ln of e, those are composing inverse functions. So I'm going to have ln of 2,000 over 807 equals 0.0241 t. And y'all, I can't encourage you enough. Well, I'll keep going, sorry. Divide both sides by 0.0241. This expression or this expression, you need to put it in your calculator, y'all, and make sure you know how to use your calculator to get the number. So t in this case is equal to 37.65. That is t. T represents the number of years after 2000. So I'm going to round that up and say that the year 2038 is when the population will reach 2,000 million. Okay, one last problem. We have the half-life of strontium is 28 years, meaning that after 28 years of a given amount of the substance will have decayed to half of the original amount. Okay? Find the exponential decay model for this for strontium 90. Okay, they didn't give me any kind of numbers. All I know is that it decays and I have to get half the original amount. So whenever you're asked for a half or a doubling, the easiest way to do it is to use the numbers 1 and 2. And so look at how you start this off. 1 is the ending amount. If I'm going half, then 1 is the ending amount and 2 is the beginning amount times e to the k, and they told me the half-life was 28 years. So what this setup says is it takes 28 years for 2 to reach to 1, which is half the original amount. If the problem said double, then you would switch the 2 and the 1. Okay? So similarly, I'm going to divide by 2 and get 1/2 equals e to the 28k. I'm going to take the log of both sides. Again, I'm composing inverse functions, so ln of e to the 28k equals 28k. Divide by 28, and I find out that k, now should stop and think, is it going to be positive or negative? Well, if it's going half, it's decreasing, so my k value should be negative. And so my model in this case, y'all, they didn't give me a starting amount because we were doing a half-life type formula. So you're just plugging in a sub 0, but you're plugging in what that k value is. Okay? And on the second part of this question, if they're originally 60 grams, so 60 grams is my a sub 0, that's the original amount, how long will it take for strontium, I don't know if I was saying that correctly earlier, sorry, strontium 90 to decay to a level of 10 grams. 10 grams. Yeah, okay. Anyway, rough day. So I'm going to start off with, and I'm going to plug in 10 for the final amount and 60 for the initial amount. So that's going to be 10 equals 60 times e to the negative 0.0248 t. You know, you got to divide by 60. And so that means that 1/6 equals e to the negative 0.0248 t. Trying to get the variable out of the exponent, I got to take the log of both sides. I am composing inverse functions here. So I get the exponent. So ln of 1/6 equals negative 0.0248t. Divide by that decimal, and I get an answer of 72.25. And in this case, that's going to tell me my answer is approximately 72 years. So that was exponential growth and decay. Y'all, the key thing is using those formulas. Plug in what they tell you and solve for what you don't know. And if you have to solve for the variable in the exponent, you got to use the logs. Thank you so much for watching, and I hope y'all have a great day.